Hello, everyone, and welcome back. We are starting chapter 6. And now, chapter 6, the big idea of chapter 6 is we know how to take the derivatives of a lot of functions. Is we can take the derivative, and we know how to do, say, polynomial functions, such as, x squared, x to the third, x to the fifth, because of the power rule, right? You also know how to do derivatives of trig functions, where that's all of sine, cosine, and because of the quotient rule, chain rule, and product rule, that actually knows all the trig functions, but maybe you have them memorized, which I think the more you do it, you will naturally memorize all these trigs. So sine, cosine, tangent, secant, cosecant, cotangent. And then you also know how to take the derivative of combinations of the functions. So combinations with the product rule, quotient rule, and chain rule. And those are very powerful things. The idea of combinations and knowing how to do trigs and polynomials, that's a lot of functions you know how to do the derivative of. And remember, derivative, and I say this because we're starting a new quarter, maybe you don't quite remember what the derivative is. Derivative, again, is what allows us to get the rate of change at a single moment of time, the IROC, the instantaneous rate of change, how something is changing at a particular moment. Now, when I say derivative, it's the entire function, meaning you can actually analyze how something is changing every single moment. But yes. Now, we know how to do these, but the big idea is we don't know how to differentiate, which differentiate is just another word for taking the derivative of something. Two things, and that is exponential functions, such as y equals 2 to the x, or we don't know how to do log functions, such as y equals log of x. And in this chapter, we're going to learn about those too. But in order to understand how to do these, it's important you first understand Euler's number, E. And that's what this video is about. Understanding what E is. A very amazing number that comes up naturally out of the world and is used in a lot of contexts. I'm going to try my best to explain it to you here. Okay, so follow along with me. Here we go. So to understand E, we're going to look at it through one of its most common applications, and that is in the finance world and investing. So let's say, for example, and some of you might already know this, I'm not quite sure because of COVID and how we ended last year, how much of you remember how to do compound interest. So we're looking at this through compound interest. So I'm going to make an example or two to help build the formula, and then we're going to use the formula to understand what E is. And it's pretty amazing. I think so. So what is compound interest? So not what is compound interest, but let's say we have, let's say you invest $500 and you're going to get a 7% rate, and we're going to compound this in different ways. So for example, 1, let's compound annually. Okay. Now how does this work again? Now compound means that you're going to get your rate, a percentage of your investment at a rate, and it's going to add on to your investment. So if I make a table here to help you visualize this of time in years and money, should have been a small parentheses there. Let's see. So in the beginning, you have $500, and after 1 year, well, you would get 7% of that. Now, what's that look like? Is you would have 500, and you're going to add on 7% of 500. Now, remember, note, percentages are concepts, not numbers. So 7% is not the number 7. 7% is equivalent to 0.07, where you always move the percent sign back 2. So a little refresh on how percents work, just in case you might have forgotten. So we could do 500 plus 7% of 500, and I believe that gives you, if I use a calculator here, 500 plus 0.07 times 500 will give you $535. Good. So that's how much you'll have after 1 year. Now, if we continue this, if we went to the second year, I could write 535 here, and I could do 7% of 535. And that will give you my answer. But to help you see a pattern, and because we're building a formula, instead of using 535, I'm going to use this right here to substitute that in. So instead of 535, I'm going to rewrite this as 500 plus 7.07 times 500 plus, and then we have, if I switch the order on these two, so if I actually write this, I do 535 times 0.07. So then that 535, I can substitute in 500 plus 0.07 times 500 times 0.07. Now this looks really messy. And maybe I missed a step, but I will clear that up right now. Back at this step right here, we could actually, instead of writing 535 right away, we could have written that as, since 500 is in both of these, we could factor out that 500 and write it as 1 plus 0.07. And that's 535. All right, so again, you can factor out a 500 because both these have a 500 there. So here I'm going to rewrite this using this instead because this is a little bit nicer. So this is 500, 1 plus 0.07. This is 500 times 1.07. And then that's timesing by 1.07. Now, what do I have here is now both of these terms have a 500 times 1.07. So I could actually factor out that and be left with 1 plus, it should just be 0.07 plus 0.07. So again, I hope you're seeing this. So that plus sign is there's two things being added here where I'm factoring out the 500 plus 1.07. And what's great about this, when I factor that out and get 1 plus 0.07, this is equivalent to 500 times 1 plus 0.07 squared. And there we're coming on to a pattern, right? So the first one after 1 year is 500 times 1.07 to the first. Second year would be 500 times 1.07 second. If I was to keep going and say the third year, well, I could just, the generic form would be 1 plus 0.07 to the third. And for n years, it would be 1 plus 0.07 to the n. And that's great, and that's helping us build the formula. But that only applies annually. What if, example 2, I compound semi-annually? And I know this is about what E is, but I want you to understand where this comes from and have a good understanding, because maybe you work in the finance world and you will understand this. And this thinking will help apply to other practices in math as well. So compound semi-annually means that if we talk about time in years and money, and I make a table of this to help you visualize it, you start with that $500 investment. Now, since it's semi-annual, you don't get the 7%. Semi-annual is like halfway in the year, so after half a year, you're going to get money back. But you're only going to get back half of that amount, so you'll get back, so it's going to be 500, and then you're going to get back half of that amount, so 0.07 divided by 2, which I know I could have written 3.5%, but I'm going to put that instead, which I could write that as 500, 1 plus 0.07 times 2 to the first. And that'd give me some answer, which I believe is, so we'll just put this in here so you can see this, 500, 1 plus 0.07 divided by 2 to the first. Did I mess up? Oh, I put 5,000. Change that to 500. And you'd be at 517.5. And then after another year passes, you now be at that amount, which I'm going to write that as this. Well, I'll write it out. 517, and then you do 0.7 over 2 times 517.5. But again, if I substitute in the generic formula from the original amount, I could rewrite this as 500, 1 plus 0.07 over 2 for 517.5, plus I could rewrite it again for this 517.5, and then you have 0.07 over 2. And now using math, we can factor out this out of both them and get 500, 1 plus 0.07 over 2, times 1 plus 0.07 over 2. You factor that out. And that's equivalent to saying 500 times 1.072 over 2 squared. Right? And that makes sense in the sense that your compound, it's the first year and you had to compound 2 times within that year. So the idea with all this is that leads us to a very common formula in math, which you might see if you ever, one day when you get older, talk about investments. I'm sure all sorts of people will be throwing this math at you, and you'll have a better understanding of how it works, or you could rebuild it, because you'll probably forget. That's very normal, but the idea is that you have the tools in your brain to rebuild it. So the formula we're going to use to understand E is this amount, where we could say the amount of investment is going to equal your principal times 1 plus, now the 0.07 was the rate, divided by n. So R is your rate, n is the number of times compounded per year. And then it's raised to the n, and then we technically have to do times t for the time that it would be. What I mean by that is, if we were to do the second year, if I squeeze that in, it would actually look like 500, 1 plus 0.07 over 2 to the 2 times 2, which you could see that that would make 4, and that's because semi-annually in 2 years would be 4 times it would compound. So this is the formula we're going to use. Okay. Now, what's the problem that's going to help us explore E? So we're going to use simple numbers here. So here it is, the big example. Let's say you invest $1 and you're going to get a 100% return. And we're going to compound different ways. Now, I know this isn't really realistic, but don't worry, it has its applications. I'm going to get there. Now, what does this look like? Okay, so if we look at the first part, let's say that you compound annually. If you compound annually, I could say that the amount is going to be 1, and then you have 1 plus your rate, which your rate, if it's 100%, is just 1. Number of compounds per year, or if it's annually, it's just 1 to the 1 times 1, because it's the number of times compound per year, 1 for annually times time. And we're actually assuming how much money you're going to have after 1 year. Let me make that clear. Money after 1 year is what we're going to be looking at. So if you do this, you'd be at 1. That makes 1 plus 2 is 2 to the first of 2. So you'll be left with $2. And that's great. All right. What if, instead of compounding annually, what if we compound semi-annually? So then that would be A equals 1 plus 1. Now, when I write this, notice that I don't need to put the 1 in front. So I'm just going to ignore that 1 in front and just start with the parentheses, and 1 plus 1 over, semi-annually means it's going to compound 2 times in a year. And that's going to be 2. And notice I'm also going to put the times 1 because we're assuming the 1 year. So that this one and that last one, I'm going to just start ignoring when I write this. If you put that in a calculator, what do you get? 1 plus 1 over 2 to the second, we'd be at $2.25. The idea that after 1 year, you've had more money. The more times you compound, you should be getting more money. But let's keep compounding. What if we compound monthly? So then that would be 1 plus 1 over 12 to the 12th, which that is equivalent to 2.613 roughly. And I'm going to go 3 numbers out, or 5 numbers out. So 61304 is what I'll do, approximately. Okay. And we're getting more money, and that's great. Let's keep compounding. Let's compound, say, daily. Okay. Now, if I compound daily, that would be 1 plus 1 over 365 to the 365, which is approximately, if I put that in, 3, 6 instead of 5, 2.714, 57. And I'm getting more money, and that's great. Let's break it down even more. What if we compound per minute? We want the best return. So that would be 1 plus 1 over 365 times 24 hours in a day times 60 minutes in each day. And then you raise it to that same amount. And after 1 year, what's that going to give you? All right, let's put this in. Should we do it correctly? So I'll add a parenthesis here. 365 times 24 times 60, add a parenthesis for the denominator, to the power of 365 times 24 times 60. And what do I get is 2.71828. 1828. In which, notice, you're getting more money, but the amount you're gaining is getting smaller and smaller. In fact, the difference between these two, between daily and minute, is not that large of a difference. Well, even better than minute, what if we compounded, infinitely many times, right? So that would be 1 plus 1 over infinitely many times to infinity. Now, we can't calculate that because infinity is not a number. So the way we calculate that is we'd have to use limits, and I'll use n here to say 1 plus 1 over n to the n. And what happens is if you do this to infinity, if you compound infinitely many times, or sometimes what they say is compound continuously, you notice that these numbers are approaching a number. And what does it approach? Well, it actually approaches 2.71828, and it keeps going. And what this is, though, is this is actually equal to what's called E. And this is very valuable. This was discovered by a mathematician named Leonhard Euler. And I know you might want to say Euler, that's how we would pronounce it typically, but it's actually pronounced Euler. And this is called Euler's number. And it has a lot of applications because notice how it just came out of a very natural problem where we invest $1 and you got your full return. So the idea is that E comes up, that number E, which is approximately 2.71828, comes up anytime we talk about anything that is growing proportional to itself. 100% return means it's your full value back. Or you could even talk about decaying proportional to itself, which is half-lives when we talk about chemistry. So that is what E is E is the exact thing for what E is it's the limit as n approaches infinity of 1 plus 1 over n to the n. The idea of compounding continuously or infinitely many times. Now, approximately, it's the number 2.71828. And it's so important that every calculator has the E button. And the E button is down here above what's ln, which we're going to talk about next lesson, on 2 videos maybe. Where if you said, what's E, and then we just say to the first, notice we get 2.71828, 1828. And now it keeps going because E is actually an irrational number. Just like pi. All right, meaning that it keeps going on forever with no pattern. We cannot stop it, which is interesting. You think about pi and that's all its applications and how that comes naturally out of nature. And that's an irrational number. Then E is the same thing coming out naturally when you talk about something being compounded proportionally to itself infinitely many times. And both of them are irrational. But this number E is so important. It's going to come in handy a lot once we get back to, that main idea of how do we do the derivatives of exponentials and the derivatives of log functions. All right? So that's what E is. Hopefully you can follow that. If you have any questions, please make sure you ask. Bye-bye.